Hey, what's up, guys? This is Chung here. So it's LeetCode time again. And today, let's take a look at 1235 maximum profit in job scheduling. Okay, another interval problem here. So you have n jobs, and where every job has a start time and end time. Also, we have a third property here, which is the profit by finishing that job. Okay, and then the constraints like this. You need to output the maximum profit you can take with no overlapping jobs. Okay, so which means that, for example, one here, we have four jobs here, 1, 2, 3, and 4, and there are like bunch of overlappings. So so end time you finish one job and start one job at the other job at the same time doesn't won't be treated as an overlapping. So this 50 and 70, it's a valid combination here. So as you can see here, so the maximum profit we can make for this example one is 120. Okay, which basically we do the job 50 first, and then we do the job 70. And here are some bunch of other examples here, right? But anyway, so we have that. So here's another example here. We have 100, but doing the 100 is not the optimal solution because we have 70 and 60 that's under 100. That's why 20 plus 70 plus 60 is the best option. All right, so that's another one. Cool. And we have some constraints here. So the constraints like this. So as you guys can see, the start time and end time is 10 to the power of 9. Okay, so it's pretty big. So keep this in mind. All right. So what's our intuition here, right? So we need to get the maximum value. So to get the maximum value, we have a bunch of options. We have binary search, right? So binary search. We have binary search. We have what? We have greedy, right? We have greedy, and we have DP. Okay. So that's gonna be our three options. We can try to solve this problem. So first one, binary search. Okay. So given like this profit, can we use binary search? Probably not, because even we know, okay, so basically given like this fixed profit, we're trying to see if we can make this profit with this kind of like those jobs, right? But to do that, we still have to do some manipulations on it. There won't be any easier process given a fixed profit, right? That's why the binary search is a no-go here. Second one is a greedy. How about the greedy here? So greedy is like, we always try to pick the best options so far at the moment. Okay, so I mean basically we will try to pick the most profit jobs, right? But the problem is that the profit is just one of the attributes here. So we also have this kind of start and end. I mean, even though let's say the profit is like 100, but if this 100 takes the longest time, this one may not be the best option so far. So basically, what this means that there won't be a clear greedy options at each moment here, just like this one, right? For example, if you're trying to use the greedy options here, of course we'll try to pick the 100 profit. But as you guys can see, the 100, even though it has the highest profit, but it takes too long. So that's why the better option is 70 plus 60. So greedy is not. Then the DP. Okay. So which means we'll use DP to solve this problem. Cool. So if we decide to use dp, right? So we define the dp of I. So how are we going to define this dp here? Um, we're gonna define the dpi equals to by the time I max profit, right? So the reason I use this definition is because, so when we know this like this DP is the DP process is finished, of course we have if we have seen all the jobs, and how can we know which job when is the ending point for for all the jobs? That's why we have to sort. We have to do the sort. We sort by the ending time. Sort by the ending time. This is another like a common strategy for all the interval problems. We always sort. We either sort by the start time or by the end time. I believe for this problem, I think it can also be solved by sorting the start time. But for me, I feel like sort by the end time is more intuitive to me because that makes this DP definition a little bit easier to understand. Basically, by the time we have the last end time of this DP, and then we know that's the answer, right? Mm, yeah. So, okay, so let's say we have DPI here, right? So we have DPI, and at the DPI here, how can we now is the time to define the state transition function, right? So at DPI here, we are at the mm, I'm sorry. So this one is by DPU by the not time I by the first by the first ice drop. Okay, by the first ice drop, the maximum profit, right? So and after sorting by the end time, and then in the end we know since we sort by the end time, so the DP the last one is when we finish our processing, right? Okay, so now the problem comes down to at the ice drop, okay, what options do we have to get to the current job? So the first one is we don't schedule the current job, right? So which means we DPI will start with DPI minus one, okay? And the second one is what? Second one is that we schedule the current job, right? So if we schedule the current job, what does this one mean? It means that we will try to pick basically with the starting point here with scheduling the current job, we know that we know the start time of the current job, right? So we're gonna have like a start time here, start time, and we know that to be able to schedule the current job, so all the previously states has to be either equal or smaller than this time here, okay? And so what's gonna be that state, right? So what's going to be that state? We need to find, basically we need to find the job. The job has the ending time who is basically the last ending, I mean, the last job that's whose ending time is either uh, equal or smaller than the start time. And then we know, okay, so that's gonna be the state we will need for this DPI here, right? So here we're gonna have like an index. So we're gonna have like index here. So this index is the last job, whose no whose end time is either smaller or equal to the start time, to this start time, right? Because why we can do that, right? Because that's gonna be the best options here because there's no point to go any way further, right? Because we know the that end time will give us the best options, right? Because even though there are like more jobs, as other job that even earlier than this job, but this one will give us the maximum answer by this moment. Basically we're trying to pick, as long as we are earlier than this start time here, we'll pick the first DP value we can find. Okay. And then we'll plus the current profit because we're scheduling the current job, right? Okay. Yeah, so basically that's the two options here. And as you guys can see here, we the end time and start time is like 10 to the power of 9. So which means that we cannot just go back from the current end time one one by one. We cannot go to the from the start time. We cannot go back to the first end time one by one because there could be a huge range of that, right? So what can we do to what can we do to find this index, right? So if we cannot uh, do a ON scan, so the option we have is a binary search, right? So why we can do that, right? Because as you guys can see here, we have a start, right? So the start here, and we have an end time. Let's say a sorted end times after sorted by the end time, and then we just need to use a binary search to find the first job whose end time is equal or smaller than this, and that index will be the DP, right? Because that DP representing by that job what's the maximum profit by that job, and that's exactly what we need. Cool. Yeah, with those being said, I believe we can start coding here. So first I need to sort all these three things together, right? I mean, I can in Python there's like a zip thing, right? Basically just zip everything here. Otherwise, if you guys using a different language like Java or something, you need to create like a new tuple or something, and then you do a sort, and then you just insert each of the index, right? You sort this by index, and then you do you create these jobs. Okay, so but here we can do an end time, and then we do a profit, right? So that's that. Okay. Okay, let me increase the font a little bit so that it's easier for you guys to see. Okay, I think now it's better. All right. So okay, so we have this, and now of course we have an n here, right? Length of the jobs. Okay, and then we need a DP, right? So the DP it's like at the beginning it's 0 because we're defining like the maximum profit by this job. So we have n in total. So and then for I in range uh of 1 to, and since we need to use like this dpi equals to dpi minus 1, right? So that's why I'm going to start from 1 to n here, and we will need to initialize dp0. So the dp0 is that by the first job, right? Or we can just do a n plus 1, but I'll just do a n here, So for the dp0, right? So the dp0 we only have one job, right? I mean, so obviously it's going to be the jobs 0. That's the first job, and the second one is a profit. It means that with the first job, the best profit, the max profit is just schedule that job. Okay, so that's that. And we have this one here. So I'm gonna jobs equals to 1.0. Okay, so we have a start time, we have a end time, and then we have a profit, right? So that's the three things we will be using later on. So 1, 2, 0, 1, 2. Okay. So here what we have, we have like the not schedule, right? Not schedule current job. If we don't schedule current job, so the DPI will be the same as the DPI minus 1. This is obvious, right? And now it's we schedule, right? Schedule current job. So to schedule the current job, like I said, we need to find the first job that's whose end time is either equal or smaller than this s. So to do that, other than these jobs, we also need like n times, right? We also need a sorted n time here. So that's why I'm going to use ended times by I'm going to create a new array here out of this job for start, end, and profit, right? In jobs. Okay, so now I'm creating a sorted list for this end job. Okay, cool. So now the binary search, right? So the binary search, so there's something we need to be careful here. So to find the best, sorry, the first one that's gonna be the n times here. So I'm using the binary search right. So why is that? Because let's say we have like 1 to 2, 2 to 4, 4 to 5, and 5 to 6. Okay, so this is a job 0, job 1, job 2, and job 3, right? So, and with job 3, as you guys can see here, so the start time is 5 and the end time 6, right? So basically we're using 5 try to find the index of 2, right? Yeah, that's why I'm using the binary search right, because the end time is like this, right? I mean, we cannot use left with this s here, because let's say if we have more than one jobs whose ending time is the same as 5 here. I mean, if we use the s here, it will go all the way back to the left to the basically it's going to skip all those kind of jobs that have the same ending time. It will be way more there. Basically, let's say we have uh, mm, we have another 5, and we have 3 here. Okay, let's say 0, 1, 2, this is 3, and this is 4. I'm sorry. Yeah, since we're sorted by the end time, right? So we have 0, 1, 2, 3, and 4. Okay, and we want to find the dp of what? dp of 3. right? We don't want to find dp of 2 because we know so those two they end at the same time, right? So that's why we need to find the last one. If we use the binary search left, you know, and we're searching 5, since we have two fives here, right? So and instead of 3 here, we'll get what? We'll get 2 because it will skip both this 5 and these two fives, and it will find the ones on the left side. That's why I'm using the right here. Basically, if we have the same 5 here, I'll find the ones on the right side, which is 4 in this case, right? And that's why I do a minus 1 here, because we need the first one on the left of this 4, which is this index minus 1. Okay. Or I think another way is, I think you can also do this. I mean, you can use left here, but if you do the left here instead of s, I believe you need to do something like a s plus 1 to make sure, you're searching the ones that is greater than all the ending times ahead of this s, right? But anyway, I'm gonna stick with my right here. So now we have this index, okay, and we just need to do this. So now the DPI is the maximum of the DPI since we have already inherits. We have a one case already here, right? So it's not schedule the job and to schedule the job. So the schedule job we have DP index, right? And then we plus P. But there's a small caveat or the small thing you need to be careful here, since we're doing a minus 1 here. The index, the binary search. So what's gonna be the index here? So it could be 0, right? Yeah. So I mean, if there's nothing on the in this list here, or we have ending time as like 4, 6, and 8. Let's say this ending time, and let's say the new ending time is what? Let's say the new ending time. Sorry, let's say the new start time. The start this one here is equal to 1. So what's gonna be? What will this index be? It'll be 0 because it finds a place to insert, which is at the beginning of this list is 0. And if we do a 0 minus 1, this thing will be dp minus 1, which is wrong. Okay. So what does this one mean? It means that we only do this dp index here if the index is greater than 0, right? If it is minus 1, then we know there's nothing to be considered, which means we just simply set 0 here, right? That's why we have this kind of like if check. Cool. So yeah, and in the end, we simply return dp minus 1, which means that we have considered the last job, and that's gonna be the answer. Okay, I'll run the code here. And it's wrong. Oh, sorry, I think I made a mistake here. So when I do the sorted here, because I thought I said we'll be sorting by the end time, but we are sorting by the start time. I'm sorry. So and we have zip, we have sorted, and then here, okay, we need to find a lambda customized key here, which will be the lambda function, right? It's going to be x1, right? That's how we sort by the second element in this new zipped list, right? And then let's try to run the code. Okay, and it's run again. Okay, well, so we have n times. Okay, sorry guys, I think many of you have already find the mistake I have made here, but bear with me. Yeah, you have to excuse me because right, typing while talking is a hard thing. Right, so So it's I here, right? Not 1. I don't know why I put 1 there. So I think this time should be right. Okay, it's a little bit better, but still not right. All right, let's see here. Mm, DP index if, oh, I'm sorry. Here, index equal or greater than 0, not greater than 0, because 0 is also fine. 0, it means that we find the first DP, right? Sorry. Yeah, let's try one more time. All right, cool. So accepted. Submit. All right, success. All right, so I think that's it. Yeah. So how about space complexity? I'm sorry, the time and space complexity. So we have assorted here. So here we have unlogin, right? That's definitely the unlogin because we sort first. And here we have like n here, right? So we have n, and yeah, that's the login, right? So here another unlogin. So in total, the time complexity is unlogin, and the space complexity is obviously is O of n, right? Because we have a DP here, and we also have this kind of jobs, right? Cool. Yeah, I think that's pretty much it is. Yeah, I mean, just to recap, right? So for this problem, we try to solve it. We tried binary search and didn't work, and we tried the greedy, didn't work either. And then we decided to use the DP to solve this problem. And the way the DP works is that we have DPI, and then we'll try to come up with a state transition function, right? And in this case, is so we define the DP as by the by the ice drop, right? So what's gonna be the max profit? And since this job has like start and end time, right? I mean, we have to be, I mean, by the last job, we have to be sure that, I mean, the other job has been considered. I mean, basically, if we don't sort by the end time, I mean, if we just randomly use the others, right? I mean, the last one may not be the last jobs, right? That's why we sort by the end time, so that by the time we are at the DP -1, we know, okay, all the jobs have been scheduled or not, right? And also from another perspective, all those kind of interval or scheduling problems, they all need to be sorted one way or the other, either by start time or by the end time. And once we sort these jobs by the end time, now we can start processing the DP here. So the first one is the 0, which is the obvious case. It's going to be the first job's profit, right? And then this is the two scenarios here. So we don't sort it, sorry, we don't schedule the jobs, or we schedule the job. This is kind of a little similar as the knapsack problem. The difference is that, for this problem, we don't have like a capacity. We only have like this, we only have this kind of like the profit, right, for this ice job. And another idea here is that, once we find the first job that's whose ending time is smaller or equal than this current start time, we know that's gonna be the DP we need to use to get the DPI here. So the reason being is that, even though there are like a bunch of k items, k before index, okay, the reason we can just use DP here instead of having a for loop here is because, this DPI, since it's sorted by the end time, and we know this index, even though we have a other index, k index or k plus one index, who is smaller than the index than the current index, but the DP index represents everything before itself, because the definition of our DP is that, by this job, what's gonna be the max profit. That's why as long as we find the first available profit, the DP or the job here, we can just simply use that DP from that index, so that we'll get the maximum profit. This is a little bit like kind of greedy uh, idea here, right? So and yeah, and another thing is that how can we handle this kind of same start and end time? So we use the right and we do a -1, okay, to get the first job, right, before this starting time. And then that's it. In the end, we simply return the last one. Cool. Yeah, I think that's it for this problem. Thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.